We're good to
Hi,
start.
everybody.
Hello.
Hello. Hi.
So I have your list of questions right here. So what I think, and there's there's no way we're going to go through all of these. So what I think we'll do is we'll start. I'll tell you a little bit about myself, and then we can answer whatever questions that you find most pressing today. Does that sound fair?
Yeah, sounds good.
Okay, good. So my name is Marcello Pavan. I'm a scientist here at Triumph, which is the National Laboratory for Particle and Nuclear Physics, located on the UBC campus. We're not part of UBC. We are operated from a joint venture, they call it, of 19 universities from coast to coast, from St. Mary's in Halifax to UVic on the island. So we're a pan-Canadian organization. We are the one laboratory in Canada where we do things like atom smashing, nuclear physics, particle physics. We do things, nuclear medicine, material science. We do all kinds of stuff. There's 500 people working here at the laboratory. Probably about, well over 100 PhD scientists working on various things. I have been here on and off. I started here as a graduate student in 1988. I got my doctorate in physics here in 1995, left for a few places around the world, including Italy and MIT for 4 or 5 years, and then came back here in about the year 2000. My primary activity these days is I'm in the communications, outreach, and education office. So I teach at UBC. I run outreach programs here at Triumph. I do various communications tasks dealing with media. Like yesterday, we had a big day Triumph got some money from the recent federal budget, and so there's a whole spend talking with media and stuff like that. I write articles for various journals about science. In the past, I've done things like I've been on The Nature of Things. I did an episode of The Nature of Things on the CBC. I wrote an episode for The Nature of Things on the CBC. I've done work on the Discovery Channel on the Daily Planet. That one was several years ago when I was younger and had darker hair. Prior to all of that, I was from Trail, like your teacher's uncle. I was born and raised in Trail, and graduated from J.L. Crowe High School in 1981. You don't need to tell me that you weren't born then. You can just keep that to yourself. And I started at UBC in the fall of 1981 and actually didn't leave. I did all my studies at UBC until I finished in 1995. So I've been doing this virtual Researchers on Call for several years now. And what I'd like to do, rather than me preaching to you about something that I'm interested in, I like to answer any questions that you are interested in. So who'd like to be first? What is one thing that really captured your interest this morning that you would like to know about? And if there's any quiet spots, I'll fill it in with one of the questions that I have that you guys sent me already. All right, so anybody like to go first?
So look at the questions that you guys had.
I'll start. So to do with pions, are pions rare, hard to find, or create?
What's your name?
Alexander.
Alexander, the pions, let's talk a little bit about what an atom is. Right? And I'll tell you how the pion fits in. Atoms, as you know, have something called a nucleus, which is really, really tiny. and electrons orbiting around the nucleus, right? Kind of like the solar system with the sun at the middle, but don't think of it that way. It's much more like a tiny, tiny, really tiny dot that you can barely see, where 99+% of the mass of the atom exists, with electrons kind of buzzing around it, kind of like fireflies around a light or something, like a fog. So that's more or less the picture, right? Is that the kind of picture you have in mind when you're thinking about atoms?
Yes.
Okay. So the electrons are connected to the nucleus with what we call the electromagnetic force. They have unlike charges. So do you know about charges already? Like positive and negative charges?
Yeah.
Yeah. So you know about that? So you know a positive charge is attracted to a negative charge. So an electron has a negative charge, the nucleus has a positive charge, and that's what keeps them together. Okay? And the electrons are going around fast, and which is why they don't, well, one of the reasons why they don't just collapse onto the nucleus. Now, the nucleus is itself made up of other types of particles, which are called protons and neutrons. So the type of nucleus is identified by the number of protons that it has. The simplest one is hydrogen, which just has one proton. Helium, for example, has 2 protons and 2 other kinds of particles we call neutrons. So helium's 2 protons and 2 neutrons. Carbon has 6 protons, 6 neutrons. Uranium has 92 protons and 130 or 140 neutrons or something like that. Now the thing about the nucleus is all the protons have the same electric charge. And if they have the same charge, you would expect like charges to repel each other. Neutrons don't have any charge. So you have this tiny, tiny, tiny nucleus with all these protons. They all have the same charge. So you would expect them to fly apart, right? Like charges repel. But they don't, because there is a stronger force in the nucleus, which overcomes what we call the electrostatic force of the protons wanting to fly apart, and keeps the nucleus together. Do you know what we call that force? This stronger force? Anyone? You'll never guess. We call it the strong force.
Oh.
Look it up. We call it the strong force. So there's a strong force, which is stronger than the electromagnetic force, inside the nucleus. And so what is that strong force? Well, that strong force is kind of a glue that holds the nucleus together. And these pions that you were talking about, the pions are that glue. The pions are the glue that holds the nucleus together. There's actually more than one kind of glue, but the most prominent one would be the pions. So the pions are in every atom except for hydrogen. So the simplest hydrogen just has one proton, but anything else more complicated than that, there's some pions in there inside the nucleus gluing the protons with each other, which would otherwise fly apart from the electrostatic repulsion, what we call the electrostatic repulsion, like charges wanting to repel, and gluing together the 2 neutrons and gluing together the protons and the neutrons. So every atom that you know of, except for simple hydrogen, has pions in it. So they're very common. They're everywhere. Now, you can't get at them because they're locked inside the nucleus. You get them out via very brute force way. So does anyone have a piggy bank?
Yeah.
Who has a piggy bank? Nobody has a piggy bank? Bitcoin? Okay, so you got a piggy bank, and if you're like the piggy banks that I had when I was a kid, there's no way to get inside of it. The only way you get inside of them is if you smash the ceramic and out come the pennies. I don't know, maybe nowadays you guys get loonies, but in my day I got pennies. So you smash the piggy bank and out come what was inside. So that's how you get the pions out. You literally smash open the nuclei of some atom, and the pions and all of the other things that were inside the nucleus gluing it together come flying out. And that is, in fact, one of the things we do here at Triumph.
Okay.
Did that answer your question?
Yes. Perfect. Thank you.
Good.
Why is electromagnetism so important to your studies and what you do?
Okay. So a laboratory like Triumph is called an accelerator-based laboratory. An accelerator is a machine that gets a particle. It could be an atom, it could be parts of an atom, it could be just the electron, it could be just the proton in the nucleus, and speeds it up to very high energies. And we speed it up to very high energies to do one of two things. One is to shatter atoms, like we did to get the pions out of the nucleus. And there's other particles in there, things called the muon, which happens when a pion breaks apart. And we also use it, so that's the kind of thing we do here at Triumph. We also shatter nuclei apart to look at all of the pieces that come out, not just the pions, but all the pieces, to try to figure out how the nucleus was put together in the first place. Because the nucleus is too small to look at with just normal light. So the only way you can look at it, because you can't really see it, is to somehow detect all of the particles that are coming out and try to figure out how they could have been put together in the first place. So that's basically what we do here. Places like you may have heard of where they discovered the Higgs boson at the LHC accelerator at CERN, is you get particles and you accelerate them to very, very high speeds. And rather than just hitting them into another atom, like carbon or something, you smash them together. So the LHC gets two protons, speeds them up to ridiculous speeds, 99.99999% of the speed of light, and then they smash them together. So, and when you smash them together at those high energies, you create all kinds of new particles, things maybe like the Higgs boson. They hope to look for other things when they start up in another month or two. Okay, so that's what accelerator laboratories do. Now, how do you accelerate these particles? And that's where electromagnetism comes in. You have to be able to get a particle, a proton, an electron, or something, and manipulate it. Hold on to it, speed it up, bend it around corners, focus it, lengthen the beam, gather a bunch of them together. The only way we know how to do that is with electromagnetism. So we could only accelerate particles that have a charge. So there will be accelerators for electrons. We're building one right now. There's accelerators for things like protons, and which is what we have here at the cyclotron. There's other accelerators for heavier nuclei like protons, deuterons, and oxygen. There's a place in Brookhaven on Long Island in New York that accelerates things like gold and lead. But all of these things have to have charge, because that's the only way that you can manipulate the atoms. We speed them up with electromagnetism, we focus them with electromagnetism, and even when we detect what happened. So I said you smash these things together and all kinds of stuff comes out. Well, how do you look at all the stuff that comes out? The only way that you can look at it is when these particles interact what we call interact electromagnetically with something. So we have various things called detectors, which can detect the passage of all of these particles and stuff that we create when they pass through them. So we can tell how much energy they have. We can try to figure out what direction they're going, what momentum do they have, are they curving, what's their mass. All of these things require electromagnetism in order to be able to figure out. That was the long answer to your question. Is that okay?
Yes, thank you.
Does that make sense?
Yes.
Okay.
That's going.
Who's next?
Is it or will it ever be possible to break up atoms and rebuild them?
We're really good at breaking them. The thing is, an atom we can break them and we can make new atoms. We actually can do that. It's called fusion. So have you heard of nuclear fusion? Yeah, so what that means is you get two different kinds of atoms. So that actually, you know what, now that I think about it, that is exactly what we do here at Triumph. So there was a question here about exotic atoms. What is an exotic atom? So this is related to your question. So I'll answer both at the same time. Okay? So atoms, the normal, what we call normal atoms or whatever, is the atoms that you can just dig out of the ground or suck out of the air. Oxygen, carbon, gold in your teeth, whatever. So, like I said before, atoms are collections of protons and neutrons with electrons going around them. As it turns out, you can't just have any old collection of protons and neutrons in the center of your atom and have the atom be stable. Only certain combinations of protons and neutrons result in a stable atom that will just stay together forever. So as far as we know, oxygen, carbon, all of these things, once you put the nucleus together, it'll stay together. Okay? There's other combinations of atoms, of protons and neutrons, however, which once you put them together, either don't stick together at all, or only might stay stuck together for a certain period of time. And then they break up. And that is what you know as a radioactive atom. So that's radioactivity for you. Radioactivity is when you have an atom, the collection of protons and neutrons is such that the atom is unstable. And so after a certain period of time, it will break up. Okay? So it could be very short. It could be microseconds, milliseconds. It could be very long. Uranium is radioactive, but it could hold together for 4.5 billion years before it decays. There's potassium in your body right now. And if you had a radiation detector, you can detect the radiation from potassium-40. It's called potassium-40. It's in your body right now. You get it every time you eat a banana. And it lives about 4 billion years before it breaks up. So it could be a long time before it breaks up, or it could be a very short time before it breaks up. An exotic atom is the general term we use for atoms which you cannot find naturally on Earth. You have to make them. So one way you can make a new atom is for the ones that don't live a very long time. Like say they only live a second. Okay? Here's one. Here's an exotic atom of sodium, which lives, I don't know, a couple of seconds. Okay? So since it lives a couple of seconds, there isn't any in the ground anymore. Because if any was made when the Earth was created billions of years ago, all of it will have disappeared by now. So what do we do here at Triumph? We want to study these exotic atoms. So what we do is we use our accelerator, we shatter a big atom, say like uranium, into lots of chunks. all kinds of chunks come flying out. Some of these chunks are just, all of these chunks are random collections of protons and neutrons stuck together. Some of these chunks are exotic atoms. Actually, most of the chunks are exotic atoms, like say sodium-21, only lives a second or so. Well, we are able now to collect all of those exotic atoms, throw away everything else, just collect the exotic atom, using electromagnetism, collect it, accelerate it, focus it, make a beam out of it, and have it collide with something else, like hydrogen. So now we broke up an atom, got a piece of it, brought it together with another atom, say hydrogen, and got them to stick together. And do you know what you get when you get sodium and hydrogen to stick together? Anyone? Probably don't know. It's magnesium. When you get sodium and hydrogen and you make them stick together, you get magnesium. And that is, in fact, how every atom in your body was created. Right? So it's a very brute force way. It's not like engineering where we can pick up one atom and pick up another atom and, go under a microscope and stick it together. But what we can do is shatter big atoms, create new exotic atoms, and have them stick together with other atoms to make even a different atom. We do that all the time here. So that's a field of research we call nuclear astrophysics. Pretty cool, eh?
Very cool.
Based on your profession, do you find yourself enjoying science fiction shows?
No. Absolutely not. So here's the problem.
Okay.
When you learn enough physics, are any of you hockey players?
No,
Anybody a hockey
one
player?
group that has no hockey players.
I follow
Okay, so-
hockey, but
Okay, so what sports do you play?
basketball.
Soccer,
Football.
Swimming and
Soccer.
basketball.
badminton.
Okay, who's a soccer player? Okay, you're a soccer player. Great. So say you're watching a movie and like these commercials on TV, and it looks like, they have kids playing soccer. But you're watching it and you're like, wait a minute, that's not soccer. And you can't, it just looks ridiculous to you because you know what soccer looks like. And you see this soccer on a commercial or on a television show or a movie, and they're obviously not playing soccer. It's a movie.
Definitely.
It looks stupid. You just can't wrap your head around it. You can't look at what they're trying to do. All you can think of is, that looks ridiculous. Like basketball. These guys jump up, and from the way they jump, they're going to go this high off the ground, right? But no, somehow they go this high off the ground and slam the basketball, and you look at that and you're like, what? You just like, it's ridiculous. So when I see a science fiction movie, any movie where science, or a television show where science is done, and I know something about that science and they do something really dumb, like it's completely wrong, I just can't stop myself from saying, this is dumb. This is ridiculous. That's not how science works. And it's difficult for me to go beyond that. Like, I know they don't care that the science is wrong. They're just trying to make a movie, right? But when I look at science fiction shows like that, I just can't, like this movie Gravity and some other stuff that's in space. They're screaming at each other. You can't hear anything in space, and all this boom and boom in space. You're like, that's ridiculous. You can't hear anything in space. And so I just can't stop myself from freaking out about the science. So I try not to watch science
Ripping your
fiction
hair
shows.
out.
Like,
It makes
not
my
even,
wife mad too, because I keep telling her, you can't do that, and that makes no sense. And she's like, shut up, just watch the movie.
like not even Doctor Who. Like not even.
Oh, Clifford, stop.
Well,
Sorry.
okay. I used to watch Doctor Who a long, long time ago. The guy who had the gigantic scarf. And some of these shows, so the science, which are so ridiculous, so there's a certain point where the science or whatever they're trying is just so ridiculous that it sort of passes a threshold, and then they're like, yeah, okay, whatever, this isn't science anymore. Then I can sort of watch it. It's those shows that try to be a little bit realistic and then fail horribly, as they all do. Those are the ones I can't stand. I'm a real science geek.
How many years of study did it take to get to where you are today?
You don't want to know. No, seriously, you don't want to know.
Is there any
Okay.
light that is...
So let me tell you, I have a PhD in physics. In general, you come out of high school, you go to university. An undergraduate, what they call the undergraduate degree, when you get a Bachelor of Science or a Bachelor of Arts or whatever, is typically 4 years. The program I went in was 5 years. And then after that, you go on to what's called graduate school. So after you finish a bachelor's degree, if you want to go into an advanced education, if you want to become an academic, go work in laboratories, you generally need, well, nowadays you almost exclusively need what's called a graduate degree. And typically here, you would go for 1 or 2 years for what's called a master's degree. So you get a master's degree in science or something like that. So that's what I did. I did a 5-year undergraduate degree. It's called engineering physics. And then I took 3 years for my master's degree. Should only have been 2, but I was playing soccer in the Canadian Championships 1 year and it got delayed. Who's keeping track?
You got it, Jenna?
Okay. And then I did my PhD. So I started my PhD in 1990. PhD degrees are, it's like becoming a doctor, but I'm on steroids. This is where you literally, you're trying to become a scientist. You take a lot of courses near the beginning, and then you're in the laboratory all the time. You have to come up with your own experiments, do your own research. You write a thesis, which is, this thick. So you got to literally write a book on a topic. Mine was 275 pages long. It's a lot of work. But if you want to become a scientist, that's what you got to do. So that typically takes about 5-6 years. For me, it took 5 years. So who's keeping count?
13 years.
13 years.
Holy cow.
And in fact, I missed one. There was 1 year after my undergraduate, I came here to the laboratory and I worked as a research assistant before my graduate degree for 1 year. So altogether, it took me 14 years. So, and that's, that is not a, so for you, that sounds insane. Okay? Because we've only been in school, I don't know what, 10 years already, or what grade are you in?
8. Probably say like
8.
9.
Oh, okay, 8. Okay, so the thought of 14 years after high school may sound insane to you. However, graduate school is not like school that you know about. Okay, when you go to university, the bachelor's degree already is very different from high school. You go to the classrooms. You're not in one building. You go to the classrooms. You have much more freedom. It's a ton of work, but it's a very different environment than high school. Graduate school is even very different. Graduate school, especially the last 4 or 5 years, is almost like having a job, like you're going to work. but you're going to work while you're studying for your degree. So it's not really like going to school like you're sitting at a desk in a classroom. It's more like you're just going to your job, and your job just happens to include taking some courses. So it's not nearly as bad as you think. Now, 14 years is a little unusual, but somewhere around 10 or 12, that's pretty typical to get to a degree like a PhD in physics. And then once you've done that, you don't become a professor. You have to do what's called postdoctoral work. And that's usually 2 or 4 or 5 or 6 years, which is kind of like what you might know as a resident doctor at a hospital. And that's where you get even more advanced training. No more school, but it's advanced training in your field. And then once you finish all of that, if you're lucky, then you become a professor or a research scientist or something.
You guys are sold, eh?
So the end, it just ends as we look.
So we probably have time for another 1 or 2 questions before they have to get to their next class, if you've still got time for that.
Why did you always excel at science in high school?
Yeah.
Yeah, straight up.
But it's the reason why I did so well at science in high school is because I loved science and learning about things. Science is what you do to try to understand how the world works. It's that simple. How does everything work? Like, why is the sky blue? Do you want to know why the sky is blue? If you're curious about how things work, that's science. And it could be how your body works, how plants grow, why do the stars do what they do? If you're curious, that is what science is, or the basics of science. And I was always, I don't know why, I was born with it. Maybe it's because of my dad or somebody else. I can't really pinpoint it, but since I was a kid, I was always super interested in science, in how things work. And so when you take the science classes in school, biology, physics, and all that kind of stuff, general science, is where you learn how things work. And so to me, it was natural. So it starts with the curiosity. It starts with wanting to figure out something. And that's what each one of you has to figure out about yourselves. What is it that turns your crank? Right? What is it that gets you excited about the world? Is it curing people? Maybe medicine is in your field. Are you curious about how things work? Maybe science is in your bones. Is it about art? This art, so maybe you're an artist or a graphic designer. Is it people? Do people interest you? Maybe then you could think about, psychology or marketing. Marketing is how to influence people. Or is it all about selling, buying and selling? You buy and sell stuff. That, then businesses. So one of the things you got to do, which is, and it's going to evolve because your mind's going to change, is find out what it is that really gets you excited, gets you out of bed in the morning, and then latch onto that. Let me tell you something. When I was a kid, so you're in grade 8, so I was grade 6 or 7, every day after school, I would go to the library and I read all the encyclopedias. Started from A, worked my way through. So Encyclopedia Britannica, you guys don't know about encyclopedias now in the internet age, but you used to have encyclopedias on the wall. And I went from A to Z, from Encyclopedia Britannica, the World Book, Collier's, all of them. I read through all of them. And then when I learned something, I went back and told my friends about it, because I loved learning about how things work. we back?
Oh, we're back.
So my friends are thinking what you're thinking. Who the hell cares about all this stuff? Right? But I love learning about this stuff and then telling people about it, what I learned. Well, and I've always had that. I've always had that. Even when I was, a scientist and I was doing research, I would still always do that, which is why I ended up in education and outreach and communications. And it turns out I'm really good at it. And that was something that I had from when I was a kid, and I kept it. And it turns out that it's a very useful skill to have, is to talk about science and explain things in a manner in which people can understand. Let me tell you, most scientists don't have that skill. So, one of the things that you're going to be figuring out is those things that you really enjoy, don't necessarily throw them away or feel that you maybe, I shouldn't be doing this because there might not be any career in it. You'd be surprised. Generally speaking, you want to exploit your talents, and your talents will lie in those things that really turn your crank, that make you excited. So you got to nurture those things, even if your mom thinks they're not going to make you any money when you grow up.
Right on.
All right.
That's great advice. And unfortunately that we're going to have to head off now, but thank you very much for your time. We really appreciate the time you've put into this, and thanks very much for meeting with us. Yeah, thanks very much.
Anytime. Anytime you want to talk to me, just give me a call.
Oh, you might regret saying that. Yeah, we might start.
Well,
if you're interested, we might.
We only got through 4 questions.
Yeah, that's okay though.
Your teacher has my email address. If you have 1 or 2 questions you really, really wanted me to answer but I didn't get to, just send me an email. I'd be happy to answer it for you.
That'd be great. Thanks very much. We appreciate
All right.
that.
Thank you.
All right, guys. Nice talking to you. Take care.
Thank you.
Bye.